Ionic cleanliness testing is a process to determine if either the fabricator of the printed circuit board or the assembler left any substances on this surface that would create issues later in the life of this product. So what we're going to demonstrate is how the process works, and then we are going to also demonstrate what happens if we add just one drop of a liquid flux to this solution. One drop over this entire area, and you'll be able to see the impact that a small amount of residual flux can have on the cleanliness of this assembly. The device beside me is generically called an ionograph, although I do believe that's a trade name. With this device, it has a solution of 75% anhydrous isopropanol alcohol, 25% DI water. That solution is a very aggressive solvent for the chemicals that are used both in board fab and also in assembly. So we immerse this particular assembly in that solution, and it immediately begins to dissolve any of the ionic substances that are on our surface. When that happens, we say the solution becomes dirty. The machine then runs that solution through a column, and that column then removes all of the things that it has dissolved from this surface. We don't know what they are because they're all aggregated together. We often call this an environmental stew. If anyone ever washed dishes, at the end of it, if you take the strainer, you'll see all kinds of things left in the strainer. The beans, the corn, pieces of beef, or whatever. That's what we call the environmental stew. We don't know what they are, but we know all of them added together created a problem for this printed circuit board if the testing tells us so. So this device washes this off, and then it cleans up the solution. As it is cleaning it up, it then is measuring all of the things it's washed, and it is giving us a figure of merit. The IPC has defined a maximum cleanliness level of 10 micrograms per square inch. But basically, it is a measure of the concentration of a specific chloride divided by the surface area of this particular printed circuit board. So every board is different, so we have a different area. What is happening is the system is cleaning up the solution of 75% anhydrous isopropanol and 25% deionized water, and it must clean it to a megohm value of 599. So we're currently at 169, so the system is cleaning up. It is making the solution pure. And when it reaches this value, we can then begin the testing. This is our pass line, the blue line here. As the solution is becoming dirty, it's being cleaned up. You can see that it is starting to give us numbers. And what we're going to do is to allow this to come to a conclusion where the curve, instead of going up, starts to become asymptotic. That tells us that we have achieved the cleanliness level. At that point, we're then going to add one drop of liquid flux. Remember, this 10 micrograms per square inch, this is our accept. At the moment, this assembly is testing very well, but it still has a positive slope. So at the point that we add the liquid flux, then we expect that this curve will take off very, very quickly. As you can see, the curve is still increasing slightly, but it's becoming more and more asymptotic. So we don't want the test to abort because it thinks that the testing is over, so we're going to add one drop of an ionic substance. What we're going to add is precisely the same liquid flux that is used in selective soldering. You can see it took only a few seconds, and now look at the change in our curve. And if we watch, we're going to see that that goes just very, very steeply. So you can see the difference in the shape of the curve if we are slowly dissolving residual ionic substances from the PCB that are part of the normal process. But if we have any liquid flux left on that surface, immediately we head to a fail limit. Remember, this is the 10 microgram per square inch limit, and as you can see, we are very quickly approaching that limit. So within only a matter of about 1 minute, this test will have failed and will show that this board, it will think is dirty. In reality, we made it dirty by adding a drop of liquid flux. And as you can see, we just hit the fail point. So we would have normally aborted this test shortly after this because the assembly failed. We've talked about cleanliness and the importance of cleanliness in the longevity of an assembly. What we're going to show you is an example of a very recent laboratory analysis that we were asked to do on behalf of a customer and the impact that cleanliness had on that analysis. So this particular assembly, which will go unmentioned, arrived, and the cleanliness testing determined there was a very high level of ionic contamination on the surface of this PCB. That ionic contamination came from the assembly process. So we then analyzed why this particular assembly failed in the field. And the very obvious reason was, if you are able to see, for example, this one pin, as I move this, I should not be able to wiggle this power connection. If we look at the back side of this PCB, you will notice that there are areas on this PCB where you see these white kind of traces. Those traces are actually created by metal migration. This PCB had an unusual set of circumstances, but it makes a very, very good example. The circumstances were PCB had a high level of ionic contamination left from the assembly process. It had traveled to the USA from Asia by boat, so it was exposed to a salt air environment. So we have moisture and salt air. It also then had the power supply connected. So this board was energized during transit. And so what happened was these white circles that you see, those are actually created by the electromotive force of the power combined with the ionic contamination that allowed an attack of the metal on this circuit board, and then it began a migration along those paths. And notice they're not a straight line. They follow whatever the level of contamination allowed these successive ionizations to happen. This is a close-up. Now again, this spray-like pattern is a migration of metal. Now if we look at this, which has this green color, that green is copper chloride. There should be no exposed copper on this PCB. It should be covered by the surface finish. However, the acid attack allowed the acid to get to the copper that is actually the base metal, and the green is copper chloride. That's why it has that particular color. And that's what's supplying the metal that makes all of these patterns. So if I look at the next example, this is a close-up of one of those pads. And again, you can see where the copper is being attacked. That's significant because what's going to happen is the acid attack is going to dissolve the copper and actually allow this barrel to separate from the PCB. Now we're going to look at the pin that I was manipulating. One, you can see in this corner discoloration of the solder of the connection, and you can see the spray pattern. But here, what is most interesting is, look, these are thermal relief attachments of that pin to the printed circuit board. They have been completely eaten by the acid attack, and you can see a migration path here. The pin and the pad have basically separated from the printed circuit board. If we look at this one, now you can see why I was able to manipulate the pin. You can see that it has protruded beyond the printed circuit board. You can see the exposed copper of the pad and the thermal relief attachment. Obviously, this is the solder, this is the pin through the solder. And if you look carefully, this is the actual plated copper barrel that went through the printed circuit board. So what we have is an absolutely perfect example of why the ionic cleanliness levels are important. We can get into a discussion of what is a sufficient or an insufficient amount of cleanliness. If I lined up 10 experts, you will get 10 different opinions. The IPC has defined a maximum level of 9.8 micrograms per square inch, or convert that, divide by 6.25, and you get centimeters square. However, that is really like a baseline. The true answer is what is required in your particular application. A baseline is simply a way in which to measure a go, no-go. But that may be way too dirty, and we use the word dirty, it isn't dirt, it's ionic contamination. That 9.8 may be too dirty for your application, or it may be perfectly fine. That is an average number for the average assembly and the average application. You may be in a medical instrumentation situation where you have incredibly tiny currents that you are measuring, picoamps, in which case that number is way too high. You may, on the opposite end, be making a toy and you don't care. So the real answer to the cleanliness level is you need to determine what is correct for your application and then apply that to your drawings as a specification.